Recording has begun, so welcome to this pre-exam class. As anticipated in my communication via email, I will solve the written exam that was given on the 11th of June 2024. The main problem in the assignment is to solve by means of structural analysis this frame. The frame consists of 3 vertical members and 2 horizontal members. So basically, before starting with the calculations implying values of loads and span, we have to solve this frame, which means from the loads, from the geometry, we have to work out the internal forces, because the internal forces will then be used for the design tasks, which are the second part of the assignment. Okay? So, first 2 points, read. Perform the structural analysis of the 2 beams, 1 and 2, by plotting the diagrams of the internal forces, shear and bending moment, as a function of P and L. Point B, reads, determine the tension forces in the ties and the compression force in the column as a function of P and L. Now you have to be very careful when you read the assignment, because the assignment implicitly tells you what you should expect in terms of solution. As a matter of fact, we have to indicate the points in the frame. This is called A, this is B, and this is C. This is point D, point E, and point F. In the description of the structure, it was written that there are 2 beams, AB and BC, the horizontal members, as we should expect, because usually beams are horizontal members. Then it was written that these 2 beams are supported by 2 ties, AD, BE, and a column CF. So, what should we expect? If a member is a tie, it means it is subjected to tension. If we call it column, we expect it to be subjected to compression. Okay? This should be found in the solution by means of numbers. Now, how do we start with the structural analysis? First of all, it is wise to look if we can find anywhere in the structure some truss members, which means members that are subjected only to an axial force, be it tension or compression. How do we find the truss members? Basically, truss member or member is a truss member if it fulfills what I call the 3 golden rules. So member has to be straight. All the members in this frame are straight. The restraints at the boundaries, restraints and constraints at the boundaries should be hinges. We have 4 members which fulfill this condition, 1, 2, 3, and 4. And there should be no loads applied in the middle of the member. So AD and BE are truss members, which means they are subjected to axial forces only. Okay? First point, as I said previously, asks you to perform the structural analysis of the 2 beams. Okay? So let's look at the beams. How do these beams look like? They have hinges at the ends, okay? Which means they are no different in terms of shear force and bending moment from a simply supported beam. So both AB and BC could be studied as regards shear force and bending moment as if they were simply supported. Okay? There is no difference as regards the flexural regime, which means shear force and bending moment. So I should expect to see in the two beams AB and BC diagrams which are no different from the diagrams I would find if they were both simply supported in this way. Okay? So let's start by working out the reaction forces. How do we work out the reaction forces? If you have a frame like this, it is wise to move from one side to the other. Namely, what happens if AD is a truss member? Sorry, I have to get something to cancel out. If AD is a truss member, I know it's subjected to an axial force only, which means that even if at point D there is a hinge which prevents horizontal translation and vertical translation, and therefore would have two reaction forces, there is only one left, which is the vertical force, which becomes the axial force in member AD. So I can replace the restraint at point D with a vertical force VD. How do I work the vertical force VD out? What is the most convenient equation to work out the vertical force VD? Move from the left to the right. I could start with a rotation equilibrium here, but it would lead to an equation which reads 0 equal to 0 because VD, or the line of action of VD, passes through point A. We move to the right, point B. A good idea is to write the rotation equilibrium MB equal to 0 of this portion of the structure, ABD. So, first equation is moment with respect to point B of ABD is equal to 0. What are the contributions to this equation? There is the contribution of VD, who is vertical, and whose distance from point B is L. So I'm simply going to put here VD times L. And by putting a plus sign there, I'm implicitly assuming, I don't have to write it, that the rotation induced by VD, which is clockwise, is positive. Then what do we have? We have a distributed load here. For the purpose of rigid body equilibrium equations, we can consider the distributed load by means of its resultant, which is a concentrated force acting at midspan equal to P times L. Okay? I'm not saying that this load is added to this. This load is the resultant force of this. Okay? What is the lever arm of this concentrated force with respect to point B? Clearly, L divided by 2. So I'm going to put here PL times L divided by 2. What is the sign of this contribution to the equilibrium equation? Since we are writing the equilibrium equation with respect to point B, this contribution is counterclockwise. Therefore, I put the minus here, and this equals 0. As you see, it's a very simple equation. It immediately leads us to determine one of the reaction forces. You can cancel out L here and L here, and we obtain that VD is equal to PL divided by 2. Let me remind you about what was written in the assignment. The two beams are supported by ties, AD and BE. If we find that VD is positive, this means that AD is subjected to tension. This is right, because I said it's a tie. Okay? What could a second equation be? We basically repeat what we did for the first member for the second member, BE. Now, if it's a truss member, it is subjected to an axial force only. So I can mark here a vertical force, which is VE. And what is the most convenient equation to write? Again, if we write another equilibrium equation here, the line of action of V passes through this point, so we will get nothing. But we have another hinge here, which can be conveniently used to work out this reaction force. So the second equation I'm going to write is the moment with respect to C of A, B, C, D, E equals 0. Because if you look at this portion of the structure, you immediately realize that the only thing unknown is this reaction force. Everything else is known.
I'm sorry, can I ask a question?
Is somebody speaking up?
Mi sente?
I barely hear you.
Can I write a question?
Write in the chat, please.
Okay.
Thank you. So, MC of A, B, C, D, E equal 0. What does this equation give us? First contribution is VD. We now know the value. What is the value of VD? It's written there, PL divided by 2. Multiplied by the lever arm. How much is the lever arm of VD with respect to C? L plus L divided by 2, which means 3 divided by 2L. And this is clockwise again. Then we have VE clockwise plus VE times what is the lever arm of VE? It's the span of BC, which is L divided by 2. You see it here. So VE times L divided by 2. Okay? Then the contribution of the two loads. First span, PL, located at midspan. The distance to point C is L divided by 2 plus L divided by 2, so it's L. Minus, because it's counterclockwise, minus PL times L. And then we have this contribution of the concentrated load on the second span. The value is PL, and it's a concentrated load. It's not distributed. The span is L divided by 2, so if it's applied at midspan, the lever arm is L divided by 4. Equal 0. I have to quickly read the chat before I solve. Why? There is a question from the audience, which is, why can't I choose only EBCF? EBCF. That's a good question. So, in the audience, somebody asks, why can't I not look to the left, but EBCF basically means looking at this portion here. The reason is simple, because I have one unknown here and a priori 3 unknowns here. So that would lead us with 3 equations with 4 unknowns. Not convenient. In order to solve it in this way, I have to add other considerations. Whenever you have truss members, it is always wise to start from them and exploit as much as possible points where you know the bending moment is 0, like hinges, rollers, things like that. I hope I answered your questions. Give me your question. Please give me a feedback if you can. Thank you for the feedback. Okay, so this equation, what does it say? This is 3/4 minus 1. It's something strange. No, sorry. 3/4 from this term minus 1 is 1/4. Again, same mistake as previously. 3/4 here. This is minus 1 means minus 1/4. Minus 1/4 means that the equation becomes V times L divided by 2 minus PL squared divided by 2 equals 0. I can cancel out L. There is a 2 which makes this term become VE equal to PL. Second reaction force. Before we go on, stop and let's think whether this makes sense. How do simply supported beams work? You remember simply supported beams? Simply supported beams, because of symmetry, a load placed at midspan goes half to the left, or I should say half to the right, if I look at my arm, and half to the left. For you, it's the opposite. So here we have two beams, which I said at the beginning are no different from simply supported beams. Load PL applied on AB goes half to point A and through tie AD. As a matter of fact, VD is PL divided by 2, half the load. At tie BE, we have half of the load coming from AB, half of the load coming from BC. So it's PL divided by 2 from the left, PL divided by 2 from the right. V is PL. PL divided by 2 plus PL divided by 2. Okay? Now we are ready to start with the free body diagram of the whole structure. We know we have PL divided by 2 here. We know we have a PL here. There is a distributed load here, which becomes a concentrated load at midspan for the purpose of equilibrium only. We have a concentrated load here, PL. How many reaction forces we have at point F? We have 3, because point F, as you see, is a built-in end. So no displacement in the horizontal direction, no displacement in the vertical direction, no rotation. 3 reaction forces. One is VF, horizontal is HF, moment is MF. What reaction forces can we use to work out these 3 equations, or these 3 reactions? Our first one is obvious. If you look at the structure, HF is the only horizontal force acting on the structure, which means if I write Rx equals 0 of the whole structure, this immediately leads to HF equal 0. Ry equals 0 for the whole structure allows me to determine the only vertical force which is still unknown, which is Vf. If you see, if you look at the structure, it's very convenient. Vf is the only vertical force still unknown. So Vf points upwards, Vf. Here we have two upward forces, PL divided by 2 and PL, so plus PL divided by 2 plus PL. Then we have two downward forces, PL and PL, which is minus PL equal 0. This leads to Vf being equal to what? 1 over 2 plus 1 is 3 over 2, minus 1 is 1 over 2, minus 1 is minus 1 over 2. To the other part of the equation, this becomes Vf PL divided by 2. Is this correct? With this upward force, this member is in compression, as it was suggested in the text. It was called a column, not a tie. Okay? Finally, MF. How do we find MF? One could start like a caterpillar and go and say, I'm going to write the equilibrium equation for rotation of the whole structure. Not a wise choice. Let's make it simple. Let's look simply at this member here, which is subjected to the reaction forces only. So I'm going to write the equilibrium equation with respect to rotation of member CF with respect to C in writing MC of CF equal 0. What do we have? HF is equal 0, does not contribute. VF does not contribute because even though it's not equal to 0, its line of action passes through point C. The only contribution is MF, and thus we conclude that MF should be equal to 0. And that's it. So even though at the bottom of column CF we have a restraint which could provide restraint both in the horizontal direction and as regards rotation, in this case the reaction forces are 0. Why? A simple explanation is that if you look at the loads, if all the loads are vertical and the structure is, like in this case, statically determined with a certain geometry layout, then the reaction forces are vertical only. We don't need to prevent something by means of horizontal force or bending moment. Okay? Another question to you. Is the value we found for VF correct? PL divided by 2. Again, back to the structure. If I said that BC is no different from a simply supported beam, the same way I judged about the values of VD and D, I should judge about the value of VF. And I will conclude that half of the load on BC goes in column CF, and half of the load is exactly PL divided by 2. Questions? Before we plot the diagrams.
Can you read the chat, please?
Again, it's difficult to hear me. Can you please re-explain this point? What point should I re-explain? Please write it in the chat because it's difficult to hear you. moment, of course. Now, I looked at the restraint at point F. It's a built-in end, so a priori it has 3 reaction forces: horizontal, vertical, moment, because all the 3 degrees of freedom are restrained. To solve and to get MF, I could start by writing rotational equilibrium of the whole structure, okay? Like I did for Rx and Ry, which I wrote on the whole structure. But it's not a wise choice because on the whole structure we have a series of different loads, and including them increases the likelihood of making mistakes. So we can make things simpler. How? We can write the rotational equilibrium of member CF only. In writing, I'm writing rotational equilibrium with respect to point C of this vertical member here. Now, if you look from this point to this member, we have HF, who does not contribute because its value is 0. Then we have VF, which does not contribute because its line of action passes through point C, so the lever arm is 0. The only contribution left is MF. MF is taken as such, it has no lever arm, it is already a moment. You do not need to multiply it by anything. Okay? In order for this member to be in equilibrium, there is no other possibility than for MF to be 0, because it's the only term left in the equation. So MF equal to 0 is what we get. And the explanation for this, if you want, it's a statically determinate structure with a certain geometry, only vertical loads applied, no need for the bending moment to be different from 0. And thanks for the feedback. Now, second point is diagrams of the internal forces of beams AB and BC. I have to cancel because the blackboard can be used only partially because of the limits of this classroom. We were not so lucky today. Probably there were some updates in the system. We have to make with what we have. So how do we look at the reaction forces and the bending and the diagrams of the internal forces of the beams? For beam AB, I will separate it from the rest. What do we know? We know its length, it's L. We know that there is a distributed load P. Do we have something at one of the two ends? Remember, we worked out VD in the first place. VD was PL divided by 2. We know the member AD is in tension, which means that at point A, what will we have from simple equilibrium consideration? A force which points upwards, which is exactly equal to PL divided by 2. Let's see why, going back quickly here. Look at this, concentrate on this. How is the free body diagram of this vertical member here? I will take it and separate it from the rest of the structure. If there is PL divided by 2 at the top, there is no other possibility for this to be in equilibrium than having PL divided by 2 at the bottom. What is this? Is this an external force? No, it's an internal force, because there is no restraint here. There is a constraint between two different parts of the structure. So the principle of action and reaction applies, which means if I then look at this point from the other side, from beam AB, what happens here? This force gets reversed in order to respect the principle of action and reaction. Look at this, and now let's go back at what I just drew. That's where this PL divided by 2 comes from. Okay? Now my question to you is, if you have PL divided by 2 here, what will be the shear force or the vertical force at point B? Sorry for that. Simply, if you have PL divided by 2 at A, and the load applied is P times L, at the second end, which is B, we will have PL divided by 2. No doubts about it. And don't get confused. This is not, and it shouldn't be, equal to the force in the tie BE. Okay? This is a part of that force. Remember what I said previously? The force in the tie BE results from something coming from the left, something coming from the right. Now, this is what comes from the left. What happens in BC? Same thing, simply that there is a concentrated load at midspan and not distributed load. If you think in the same way starting from point C, by looking at the column CF and what it has, you will realize that you will have PL divided by 2 at C and PL divided by 2 at B. Okay? Simply applying the principle of action and reaction at point C, as I did previously, and then looking at the equilibrium of B in BC to find what happens at B. Now, if you look at these two free body diagrams, you realize what I said at the beginning. These two beams are no different from simply supported beams. If you had solved them with a hinge and a roller, you would have obtained the same values of the reaction forces. Got it? If this is the situation, what do the diagrams of the internal forces look like? Without doing any calculation, first we imagine what the diagrams will look like. In a beam with a distributed load, shear force will be constant, linear, parabolic, cubic. What? Constant. Not constant. No. Linear. Will there be discontinuities in the shear force diagram? No, because there is no concentrated load applied in the middle. What will the bending moment be? As I said during the classes, there is a mathematical relation between bending moment and shear force. You don't need to remember this. You need to remember that if you have a distributed load applied, bending moment diagram is expected to be parabolic. What happens in a beam which has a concentrated load? Now the concentrated load leaves you with two halves of the beam which are unloaded, which means shear force is constant, but the presence of the concentrated force makes the shear force diagram discontinuous. So what you have to add is that the diagram will be piecewise constant. And I'm going to make it short by writing PSW constant. So I expect to have a discontinuity in my shear force diagram. At the moment, again, with two portions of the beam unloaded, I expect the two halves of the beam do not have loads. There is only one load in the middle. So the bending moment should be linear. The fact that there is a load concentrated at midspan makes the moment piecewise linear. Okay? So not one straight line from the beginning to the end, two straight lines with a discontinuity of the slope at midspan. Got it? Before doing any calculation.
Can you read the chart, please?
It's not OCW, it's PCW. PCW, which means piecewise. In Italian, a tratti, which means shear force is piecewise constant, diagramma di taglio lineare a tratti, costante a tratti. Piecewise constant is costante a tratti, con una discontinuità. E invece, at the moment, piecewise linear, in Italian, lineare a tratti. Which means, not for the bending moment, for example, not one straight line, but from the beginning to the end, two straight lines with a discontinuity in slope where the load, or the concentrated load is applied. Okay? So, as we always do, I will now redraw the structure in order to plot the shear force diagram, which in my conventions is positive if clockwise. What does the shear force diagram look like in beam AB? Back to beam AB. First point AB, force is upwards. If you look at my sign conventions, a point located to the left upwards is positive. So shear force at point A is positive and the value is PL divided by 2. At the right end, my shear force is positive if it points downwards. What happens at point B? Shear force is PL divided by 2 upwards, which means it's negative. So if the first end is positive, second end is negative. These are the two limit points of the shear force diagram. Again, PL divided by 2. What is the trend in the middle? You don't need to work out the complete equation. You know it's linear. You simply draw a straight line connecting the 2 points. And you put the plus here and the minus here because all the first half span is positive, all the second half span is negative. Same thing for BC. Remember the conventions, left hand positive if upwards. What happens at point B in BC? It's upwards, which means, again, PL divided by 2. Same value. What happens at the second end? Second end, positive if downwards. But at BC we have an upward force also at the second end, which means second end has a negative shear force. I mentioned that the shear force in this beam should be piecewise constant, which means constant in the first half span, constant in the second half span. What happens at the middle? We could demonstrate it by equations, but we know it from what we did during the course. If you have a concentrated load, the shear force diagram has a discontinuity, which means a jump, which is exactly equal to the value of the shear of the force applied. So there should be a discontinuity at mid-span, which means the diagram is like this. This portion is positive, this portion is negative. This discontinuity, the value of this jump, is exactly equal to PL, which is the concentrated load applied. Got it? Very good. Now, for a person who asked in the chat, can you see what piecewise constant means? Constant in the first half span, constant in the second half span. So both portions are constant, but with different values. One is positive, the other is negative, and therefore there is a jump at mid-span where the concentrated load is applied.
Thanks.
Okay, now we need to work out the bending moment diagram. Both in the case of beam AB, where the diagram is expected to be parabolic, and in the case of beam BC, where the moment is expected to be piecewise linear, we cannot get away with just 2 points where we know the bending moment. We need 3 points. We don't need, again, let me underline this concept. We don't need to work out the whole equation of the bending moment diagram. It's enough to have the minimum number of points required to plot the diagram. In the case of a parabola, if we only have 2 values, there are infinite parabolas which pass through 2 points. We need 3. So how do we choose the third point? The wise choice is to work out the moment at 1 point, which is then important for design. So the point of maximum bending moment. What is the point of maximum bending moment? Shear force is 0. Where is the shear force 0? At mid-span. Same way of thinking for BC. We already have 2 values of the bending moment available, where at the ends, B, C have 0 bending moment. We know because there are hinges there. We need a third value of bending moment. Where are we going to work it out? Mid-span. So, also in this case, moment is calculated here. Okay? I'm going to do it here to save some space. Sorry. So for BC, for AB first. Max bending moment is worked out how? I draw half of the beam, L divided by 2. I know it's subjected to a distributed load. I can look at the beam starting from the left or starting from the right. I'm going to start from the left, so this means this point here is A, where we know the shear force is PL divided by 2, which means that this point is midspan of beam AB. I expect it to have a positive bending moment, which means a bending moment that has tension at the bottom. Do I need to put something else at the ends? At the first end, no, because there is a hinge, so there is no bending moment. At midspan, no, because we know there is a bending moment. We know the shear force is 0. Okay? Which is the most convenient equation we can write on this beam, since we want to have MAB? Since the shear force here is 0, okay? Most convenient equation is MA equals 0. So I'm going to write rotation equilibrium with respect to this point. We have the contribution of the distributed load, whose value is P times L divided by 2, with the lever arm, which is how much? L divided by 2 divided by 2, which means L divided by 4. And this is clockwise. And then we have minus MAB equal 0, which immediately leads you to MAB equal to PL squared divided by 8. The well-known value of the maximum bending moment in a simply supported beam subjected to distributed load. PL squared divided by 8. We found it also several times during the course. What happens with BC? Same way of thinking. We start from the left. Point B, we have PL divided by 2. We know. We get to midspan, where there is moment BC, MBC. How much is half of the beam? In this case, it's L divided by 4. Careful about one thing. In this case, I cannot say that the shear force here is 0. It's not 0. There is a discontinuity. It doesn't make the shear force be equal to 0. It means if you move slightly to the left from midspan, it has a value. Slightly to the right, it's another value. They are different in sign, equal in value. But the shear force here is not 0. So I should include, if I look at the whole free body diagram, the shear force here. For example, like this. I don't want to include this in the equation, so I'm going to write the rotational equilibrium with respect to this point, starting with MBC. MBC is counterclockwise. Then we have the contribution of the shear force at the first end, at end B, which is PL divided by 2, minus PL divided by 2 times L divided by 4. So again, MBC is equal to PL squared divided by 8. This is the maximum bending moment in a simply supported beam subjected to a concentrated load whose value is PL and whose span is L divided by 2. Okay? Check what we did in class. Given that we changed the value of the concentrated load from capital P to PL and the span from L to L divided by 2, the value is consistent. Okay? So I presume you have written down the result. I will move back to my board with the diagram. I need some space. This is the shear force diagram. For the bending moment diagram, you know you cannot specify positive and negative conventions. What you have to specify is whether you plot your diagram on the tension or on the compression side. I'm going to plot it on the tension side as it is customary in Europe. But again, if you specify you want to plot it on the compression side, no problem. Let's fix the values we already know of the bending moment. Where are they? The hinges at the ends of beams AB and BC. So this point, and this point all have zero bending moment. Got it? If you have a solution where the bending moment is not zero at hinges, passing hinges, I mean hinges which look like circles, not the half hinges for the continuous beams, okay? Hinges like in this case, and the bending moment is not zero, you have something wrong. You have to check your results because something is wrong. Then, what values do we have? We have the value at midspan. How much is it? PL squared divided by 8, first span. Then, PL squared divided by 8, second span. So, the two beams have the same value of maximum bending moment. What do the diagrams look like? First one is parabolic, which means I have to draw a parabola which passes through these 3 points. The second is piecewise linear, which means this is the bending moment diagram of the first span. This is the bending moment diagram of the second span. Okay? What do you say we take a short break in order to get some coffee, water, or whatever? So I will resume in 10 minutes, okay? So now we'll move to the second part of the assignment, which was concerning the design of the members and which implied to replace the symbols with numeric values. Note that I plotted the shear force and bending moment diagram only because basically the diagram of the axial force is related only to the axial forces in the ties, in two ties and in the columns. So it basically consists of 3 rectangles which shouldn't pose a problem to any of you. First task of the second part of the exam read: design the section of beam AB at SLS, which means serviceability limit states, assuming an IB section by limiting the maximum displacement at midspan to Vmax equal to L divided by 300. What does this mean? This means, and for this you had to take advantage of the design aids provided with the written exam. On the basis of the following structural scheme, it represents a simply supported beam with a distributed load. B on span L, where the bending stiffness of the beam is indicated as EJ, once again, product of modulus of elasticity by the second order moment of area in the direction of the bending. Then this means that there is displacement at midspan, which is V max equal to, this was provided in the design aids, okay, which is equal to 5 divided by 384 PL to the power of 4 divided by EJ. Now this number, which clearly depends on the numeric values which were assigned, has to be worked out, and it has to be lower than L divided by 300. This is a typical displacement limitation which is provided in structures. Now, this first part depends on load applied, span of the beam, modulus of elasticity, and second order moment of area. This is a requirement, okay? How do we design the beam? What is the degree of freedom we have to design the beam? Everything is known, P is known, L is known, the modulus of elasticity was provided, equal to 200 gigapascals. The only quantity we have to work out is second order moment of area, which then determines what your beam section will be. Okay? Let's do it. We rearrange this equation in order to determine a condition for J. So basically, I take J and I bring it to the other side. I take everything that is on the second side and I bring it to the first side. So the condition, the design condition becomes J greater than 300 divided by L times 5 over 384 times PL to the power of 4 divided by E. The value of L can be cancelled out. And now we have to replace for the numeric values, which I'm going to write at the top right, close to this structural scheme. L is equal to 4 meters. The load at the serviceability limit states, which I'm going to indicate as PSLS, is equal to 40 kilonewtons over meter. And as I said previously, the modulus of elasticity is 200 gigapascal. We don't need anything else. That's as complicated as it gets. So we simply have to replace for the numeric values with the correct units of measure. Now, my suggestion to you is, of course, you are free to work as you like. My suggestion is bring everything to newtons and millimeters. Okay? So, these are numbers, so I can simply do the multiplication or simplify it. It's not needed, but 300 times F over 384 becomes 125 over 32, just to give you how this fraction of numbers reduces, but you don't have to do that. I mean, you simply calculate it. Then P, 40 kilonewtons over meter. How many newtons are there in 1 kilonewton? 1,000. How many millimeters are there in 1 meter? 1,000, which means 40 kilonewton over meters is equal to 40 newton over millimeters. This is useful to know. So the load here is 40. Then we have L to the power of 3 in millimeters. 4 meters, how many millimeters are they? 4 meters are 4,000 millimeters. So here, 4,000 to the power of 3 divided by E. Now E is slightly more complicated. 200 gigapascals is 200 to the power of 9 multiplied by 10 to the power of 9, which means billions pascals. That doesn't help a lot. It is better to see that this number is equal to 200,000 megapascals. Why? Because megapascals are Newton over square millimeter. Newton over square millimeter. So here I'm going to put divided by 200,000. And now we do the calculation. You can do it with me. I'm going to repeat it on my calculator. Simple hand calculator, that's all you need for the exam. Doesn't get more complicated than this. So 125 divided by 32 multiplied by 40 multiplied by 4,000 to the power of 3 divided by 200,000. This leads to 50 multiplied 10 to the power of 6 millimeter to the power of 4, which is the unit of measure for a second order moment of area, which is a length to the power of 4. We're going to transform this into centimeters to the power of 4. Why? Because the tables provided as design aids were in centimeters to the power of 4. How do I move from millimeters to the power of 4 to centimeters to the power of 4? There are 10 millimeters in 1 centimeter. There are 10,000 millimeters to the power of 4 in 1 centimeter to the power of 4. Which means basically I have to divide this by 10 to the power of 4, which leads to 50 times 10 to the power of 2, which is 5,000. Okay? So my design equation, let's go back where we came from, implies that the beam is correctly designed if my second order moment of area is larger or equal than 5,000 centimeters to the power of 4. I will now quickly share the screen. You in the classroom have the design aids, can check it together. Just quickly sharing the screen for the people at home and for the recording. These were the design aids. You should see them at home. Here the coefficient for the simply supported beam, basically the one I started from. You should turn it around. You're looking at the wrong side. Can you see at the top of the page the coefficient we used? These are the geometric properties of the IB beams. Here you have in the second column, depending on the section type, the second order moment of area in centimeters to the power of 4. what will the correct section be? IP 270, which is the first beam that has a second order moment of area who is larger than 5,000. Okay? I hope you could see it at home. I hope it stays in the recording. That's basically how it's done. As you see, calculation is not so complicated. You just need to put things down the proper way and then correctly convert the units of measure. Okay? What might change in different written assignments? For example, the structural scheme may not be this, it may be another one, for example, with a concentrated load in the middle, but the value here is provided. What can change? This value here, L divided by 300, we explained it during class. This depends on what you are designing. If you are designing a bridge, maybe much lower, the displacement, which means this coefficient here much higher, L divided by 500, 600, something like that. Okay? The procedure is always the same. That's how you design for displacements. The driving parameter, the driving quantity is second order moment of area, since we are talking about bending. These are deformations and displacements induced by bending. Now, I should delete my bending moment diagram, but I will leave it because the second point of the second part deals with checking the bending capacity of beam BC at ULS. So the question here is different. We are looking at this beam and we are asking ourselves, since it is designed, and what is it? It was in the written assignment. Beam BC has a section which is in, it was in the drawing, it's an IPE 220. We ask ourselves whether this capacity is enough. And since it specified bending capacity, the question is about the bending moment. What is the maximum bending moment in beam BC? We worked it out previously. You see it there, PL squared divided by 8. Now do not get confused. Even if here there is a span L, this L here is not this span. It's the symbol which represents the span of the first part. Okay? It's a symbol, L. This L here, it's the same as here, so it's always the length between A and B. Okay? So how much will it be? With the values provided in the assignment, the load at the ultimate limit state was 60. So 60 kilonewton meters. Then there is the length. The length was, as previously, L4 to the power of 2 divided by 8. And you see the 4 here, it's the length, it's the same as previously. Again, even though we are at span BC, the symbol L refers to the length of AB. It's a symbol. Okay? P is different. Why? Because previously we did the design at serviceability limit states, so we were concerned with displacements, serviceability. Okay? Here we are asking ourselves whether the bending capacity is enough. So the load is higher. How much higher? 50%. 60 is 40 times 1.5. 50% higher. Makes sense. Okay? 60 times 4 to the power of 2 divided by 8 is 120 kilonewton meter, which is the customary unit we use for bending moments. force times length. Got it? Now, this is the moment which acts on my beam, okay? It's the maximum moment that the beam has to sustain. Question is, with this section, will it be enough or not? To answer this question, we have to remind or remember how the maximum bending moment of a section can be determined. We will call it resisting bending moment. In symbols, it is the design yield strength, which means the maximum stress the material can sustain, times a section modulus, which is usually indicated by WPL. PL stands for plastic, because we're doing a calculation in the plastic range. Where does this come from? It's given. FYD is 200 megapascals. Where does this come from? From the same table we just looked at, which is a table for IB sections. So we have to first ask ourselves whether the IB 220 section is enough. So I'm going to change to the other blackboard. How do we do that? First, I create some space. Quickly sharing the screen, you look at the tables, please. In the case of this second assignment, I'm not looking at the second column with JY. I'm looking at the third column with WPLY. And at the line of IB 220, I read a value which is 285.4. Okay? This is the value. Now, so for IPE 220, WPLY is equal to 285.4 centimeters to the power of 3. Which means, again, do the calculations, 285,400 millimeters to the power of 3. Okay? What will be the resisting bending moment? Again, FYD times WPLY, 200 megapascals, which are Newton over square millimeter, times 285,400. You do the math. The number is 57 millions and something like that. So 57.0810 to the power of 6 Newton millimeters. How to translate it into kilonewton meters? You simply divide by 1 million, so 57.08 kilonewton meters. Question to you, is the section IPE 220 enough or not? Is 57.08 larger or lower than the moment applied? 57.08 is much lower than 120. So I now have to redesign the beam section. How? Instead of doing trial and error, since the calculation is direct, let's do it like that. WPL minimum has to be larger than what? MBC, bending moment applied at ULS, divided by FYD. So, let's try it. What is MBC? You have it, we just saw it, 120 kilonewton meters. In Newton millimeters, it's 120 times 10 times 10 to the power of 6, divided by FYD, which is 200. Let's do the math. 120 to the power of 6 divided by 200. Result is 600,000 millimeters to the power of 3. Our table is in centimeters to the power of 3. How do we translate? We simply divide by 1,000. How many millimeters, how many cubic millimeters are there in 1 cubic centimeter? 1,000. So this leads to 600 cubic centimeters. Again, table. What is the first section which fulfills the requirement as concerns the section modulus? As you can see, IP 300 has a section modulus which is 6 to 8.4 cubic centimeters. And therefore, our choice is to redesign the beam with an IP 300 section. Oh, I just saw now that there was a question from the audience. Where did I take 5 divided by 384? As you saw, it was in the design aids. So it's basically a coefficient that depends on geometry, shape of the load. But whenever you have to solve such a task in the written exam, it is provided to you as a design aid. And I hope I answered your question. Okay, sorry for not seeing in due time. Probably you understood it while I was doing it. Now, last but one assignment, design the section of tie AD at ULS, okay? Tie AD at ULS. Go back in your notes, take back the part concerning the structural analysis, and the first thing we did, which was determining VD. Now VD is the reaction force at point D, but it is also the actual force in the tie to the left. So remember, we solved this, there was beam AB with the distributed load, and then the rest of the structure, whatever, okay? I started by working out VD, which is PL divided by 2, which is the force in the tie, okay? Now, the assignment says we have to design a section of this tie at ULS, assuming a circular section with an even diameter, which means the section of this AA is a circular section with even diameter, which means 10, 12, 14, 16, like this, okay? Not 13, not 11. Why do we only have even diameters and not even and odd diameters? Because if you only have 1 millimeter in difference, you cannot tell the different bars one from each other because the difference is too low. You cannot see it with the naked eye, differently from the case where you have 2 millimeters. Maybe easier to understand or to distinguish it. So VD equal to PL divided by 2. What is P? We know at ultimate limit states, we just saw it for beam BC, it's 60 kilonewton over meter times the L. What is the length? We already saw it many times, it's 4 meters. and then divided by 2. 60 times 4 is 240. Divided by 2 is 120 kilonewtons. This is the force acting on the tie at the ultimate limit states, which means, to put it in a simple form, this is the maximum load the tie has to withstand in the most unfavorable condition. So we have to design the section for this situation. What is the maximum axial force a tension member can sustain? Very simple. Yield strength of the material, FYD, times the area. Okay? For our case, we know that Nmax has to be larger than Vd in order to be a properly designed member. What is the design parameter in this case? We have the yield strength, we have the acting axial force. The only design parameter is the area. So the minimum area is equal or greater equal than Vd divided by Fyd. What is Vd? Here, 120 kilonewtons. Again, put it in newtons. 120,000 divided by FYD. Yield strength, design yield strength, 200. Equal to what? .600 square millimeters. So we have to find a circular section whose area is larger than 600 square millimeters, under the requirement that the diameter of the circular section is an even number. How do we do that? I need some more space. I will get it here. How is the area of a circle? If d is the diameter, the area of a circle is P times d squared divided by 4. In our case, this has to be equal to 600 square millimeters. Let's do some working out. Here, 600 square millimeters equal to this, where you clearly highlight the diameter. What does it lead to? It leads to d minimum is equal to square root of what? 4 times 600 divided by P. 4 times 600 divided by P. I will do the math for you. Result is 27.63. Unit of measure is millimeter. What will our choice be? The result is 27.63, and we want an even diameter. It should be 28. So final choice is this 27.63 becomes 28 millimeters. Okay? Answer to the last but one point is diameter 28 millimeters. Very last point now. Check the section of column CF at the ultimate limit states, assuming an HEA 40 section and h equal to 3 meters. H is the length of the column. To correctly evaluate the buckling length, consider whether the displacements and rotations at the two ends of the column are restrained or not. We need space. We definitely need space. This is clearly a problem involving buckling. As a matter of fact, the buckling length is explicitly mentioned. So let's look at the frame we are considering. You know, there is a tie, there is a beam, another beam, and then we have our column with a fixed end. Now, regardless of the loads, we have to ask ourselves how the two ends of the column are restrained. As regards the bottom, there should be no doubts about the fact that it is built in. As regards the top, the question is, can it rotate? It can clearly rotate because there is a hinge. So the top of the column is free to rotate. No restraint as regards rotation. The more complex question is, can it displace? Apparently, some may think it is restrained by the rest of the structure. But is it? If you have a tie here and a tie here, basically, the structure is like a seesaw, which is suspended on, if you're thinking about ties, these members can be replaced by wires. They could be wires, which cannot prevent in any way lateral movement. Okay? As a matter of fact, they cannot prevent lateral movement. Why? Because they are unable, being truss members, to sustain, for example, horizontal loads. If you place whatever horizontal load on the structure, it will move through the beams and then inside the core. Okay? It is not so simple, but I just made it simple. Which means basically this is free to displace in horizontal direction, free to rotate. So what will the buckling shape look like for this column? With the displacement of the top point, it will buckle in this way. And if this buckles in this way, the frame will, at incipient buckling, it will displace like this, okay? This is the deformed shape that will be induced by the buckling of the column. Now, if this is the shape, what is the buckling length? If the length of the column is h, the buckling length will be h, which means 6 meters, because the assignment said h is 3 meters, okay? Now, how do we check for buckling? In this case, it was provided that the section was HEA 140, okay? So the first thing we have to remember is how a compression member is designed. Let me quickly share my screen. If we go further with the design aids, in the second part, in the second sheet, there was geometric properties of HEA column, cross-sectional area, and 2 second-order moments of area with respect to the 2 axes. And here there is the actual capacity of compressed members. This is an interesting equation, FYD times A divided by omega, where omega is coefficient that depends on the slenderness of the member, provided in this table here. So now let's go step by step, and then we will go back to these design aids. So the maximum axial force in a compressed member is Fyd times A divided by omega, where omega is a function of slenderness whose symbol is lambda, Greek letter for L. Okay? So first thing to do is to calculate the slenderness, and this you have to remember what the expression for the slenderness is. In case you don't remember, you ask me during the exam. Slenderness is defined as L0 buckling length divided by radius of gyration I, small I. Now the radius of gyration is defined as the square root of second order moment of area divided by area. In our case, we have 2 second order moments of area. We just saw them. Geometric properties of the HEA 140 section are area and 2 second order moments of area. Which one do you take for doing the check? It is conservative to assume to do the check with the minimum value of the second order moment of area. So I'm calculating the radius of gyration, which is the minimum, which means based on the minimum value of the second order moment of area. Quickly back again to sharing my screen. So if these are the geometric properties, what value am I taking? I'm taking this one, the lower one, which is called JZ, for bending about the weak axis, as we said during class. And here is the area. So remember the value, 389.3, and the area is 31.42. So in our case, the minimum radius of gyration is square root of 389.4 divided by 31.42. I do the calculation for you. The result is 3.52 centimeters, since all the geometric properties were in centimeters. What do we calculate now? I will take some more space here. Sorry. From the value of the radius of gyration, we calculate slenderness. And since we use the minimum radius of gyration, this will be the maximum slenderness of the member. L0 divided by I min. How much is L0? We see it here. Buckling length is 6 meters. How many centimeters? 600 centimeters. Divided by 3.52. How much is this slenderness? $85.2, which I'm going to round to 85. Dimensionless number. Lambda is a ratio between length. It has no dimensions. It's a pure number. Okay? From this value of slenderness, I can work out omega corresponding to this maximum slenderness. Slenderness is 85. Quickly sharing the screen. You go down to find the omega value corresponding to 85. Here, you have to go down the first column where you find the value 80 and then move to the right. The first number is 80, 81, 82, 83, 84, 85, which means the value corresponding to lambda 85 is 1.37. Now we have all the ingredients we need to calculate Nmax. What is the maximum axial force our column can sustain? FYD, yield strength, 200 times area. We have it in geometric properties. I will not share it back. You can look it up. Confirm it's 31.42 square centimeters. So it's 3142 square millimeters divided by 1.37. What's the number? The number is 458,000 newtons, which means 458 kilonewtons. Seems a little bit high to me. We'll quickly do a check. Seems I did something wrong. Yes, I did something wrong. I get the wrong value of, I don't know why. I probably forgot to multiply by 2. So this value of slenderness is 170. The value of omega becomes 3.72. And the final value of the axial force becomes 170 kilonewtons. Sorry for the mistake. Should have realized previously, but the procedure is correct. Okay? Now my question to you, is this enough or not enough? How much was the force, the actual force acting in column CF? Remember, subjected to compression equal to PL divided by 2. Which, as in the case of tie AD, is equal to 120 kilonewtons. So, the force in the column is 120 kilonewtons. Is the section properly designed? The answer is yes, because 170, the maximum axial force this member can sustain in compression, is larger than 120. I will now stop the recording. Thank everything for your patience. Thank everybody, sorry, for your patience, and we will have some more space for questions and answers.